Hello everybody, Mastermind here again. So today we're going to talk about an important organic reaction known as aldocondensation. Now, this reaction is very important in organic chemistry in the fact that it's formed the basis of so many type of reaction undergone by an important functional group in organic chemistry known as carbonyls. Carbonyls, which are either alkanals or what we call aldehydes, and then we have alkanone, or we call what? Ketones. Now, an aldo, the word aldo is basically a molecule that contains two carbonyl groups. The word aldo is a molecule that contains two carbonyl groups. Now, the two carbonyl group can be both alkanals, both aldehyde, and both alkanone, or can either be an alkanone and an aldehyde. Now, it's important to note that not all alkanals or not all carbonyls can undergo aldocondensation. When you want to carry out an aldocondensation reaction, you need at least one of the carbonyl having what we call an alpha hydrogen. An alpha hydrogen. I'll come again. Not all carbonyls can undergo aldocondensation. For an aldocondensation reaction to occur, you need two carbonyls, of course. Now, out of those two carbonyls that you need, one of them must have an alpha hydrogen. Now, what do you call an alpha hydrogen? An alpha hydrogen is an hydrogen that is attached to an alpha carbon. So the next thing is, what is not an alpha carbon? An alpha carbon is any carbon that is connected directly to a carbonyl carbon in an aldehyde or an alkanal or an alkanone. Let me give what I mean. Let's take this to be a ketone, right? Let me use CH3, CH2, C double bond O, CH3. Let's use this as a case study. This is a ketone. Why is it a ketone? Because the carbonyl group is not at the terminals. It's anywhere else on the terminals. Now look at this carbon. Now this carbon is, if you draw this in a straight chain, you have this. You have CH3, CH3, CH2, then you have C double bond O, you have CH3. Now look at this. This is what we have here in the Fischer formation. Look at this carbon. Let me number the carbon with alpha. Let me label the carbon with alphabet. We have carbon A, carbon B, carbon C, and carbon D. Now, carbon C is a carbonyl carbon. That's a carbon that has the Cu group. Now, carbon C is connected to carbon B and carbon D, right? Now, any carbon that is connected to a carbonyl carbon in a carbonyl structure, that's either aldehyde or ketone, that carbon is called an alpha carbon. So any carbon that is connected to the carbon that bears the Cu group is called the alpha carbon. So in this structure, carbon B here is the alpha carbon, it's an alpha carbon. Carbon D is also an alpha carbon. Now, any hydrogen that is attached to an alpha carbon is called an alpha hydrogen. So in this structure, these hydrogens that I'm going to mark, this, and this, they are called alpha hydrogens. And that's because they are connected to an alpha carbon. Now, any carbon that is connected to an alpha carbon in a carbonyl, that carbon is called a beta carbon. Any carbon that is attached to an alpha carbon in a carbonyl structure, that carbon is called a beta carbon. If you look at this structure, carbon A is attached to carbon B, and carbon B is an alpha carbon. So it means that carbon A will be a beta carbon, and so on. Now, what you should also note here is this, that any carbonyl, either aldehyde or ketone, that has an alpha hydrogen. Any carbonyl, either alkanal or alkanol, that has an alpha hydrogen, in that it means that it has an alpha carbon. Those carbonyl, either aldehyde or ketone, are said to be enolizable. They are said to be enolizable. Now, meaning that they can form an enol. Now, an enol is basically something that has double bond and OH. And typically, most enol are nucleophiles. Most enol are nucleophiles because they carry a negatively charged atom, usually carbon, charged carbon. As if you want to bring it down to just carbonyls. So the gist here is that, or the information here is that any carbonyls, either aldehyde or ketone, that has an alpha hydrogen is said to be an enolizable carbonyl. Note that. Now we have already started aldocondensation reaction. I'm just going to give you the important information you need to know for you to understand this. Now coming back to the aldo term. Now I said an aldo is a structure that is made up of two carbonyls. Can be either alkanal and alkanal, alkanone and alkanone, or alkanal and alkanone. So it means that we have two types of aldo reaction. Generally, we have the self-aldocondensation, like I usually call it, and we have the cross-aldocondensation. So self here basically means between two carbonyls of the same group. That's between two alkanals or two alkanone. And then cross is between an alkanal and alkanol. Remember that for aldocondensation to occur, at least, in fact, one of the carbonyl must have an alpha hydrogen. Now, let's now define what an aldocondensation reaction. Now, in a very simple term, an aldocondensation reaction is a reaction between two carbonyls in which one of the carbonyl must have an alpha hydrogen, that is, it must be enolizable in order to produce a molecule that is formed from the two carbonyl group known as an aldo. Now, that molecule known as an aldo is also called a beta hydroxy ketone, an aldo. As when you merge two carbonyl compound together, you get an aldo. An aldo is also called beta hydroxy ketone, or it is typically formed from beta hydroxy ketone. Now, aldocondensation reaction proceeds through nucleophilic attack, or you can say nucleophilic addition. And this is very, very important. And this is because you have the presence of an enol created during the reaction. And you remember that one of my videos I posted that carbonyls, the major reaction in undergo is nucleophilic attack, and this is due to the presence of an electrophilic carbonyl carbon. So it means that for an aldo to proceed, you must be able to form an enol or an enolate. That's, you must be able to create something that has a negative charge. Remember I wrote that enols usually have a negatively charged atom or carbon, and this is what makes them a nucleophile. So for an aldocondensation reaction to proceed, you actually need a strong base. A strong base. So strong bases like sodium hydroxide, even hydroxyl radical, also a strong base. But the two I like using is either sodium hydroxide or hydroxyl radical. So aldocondensation reaction requires strong bases, a strong base, e.g. we have sodium hydroxide, the common way of writing it in most cases will be sodium, think OET. We also have hydroxyl radical, hydroxyl radical, which is written as OH, yeah, and then showing the bonds, the Lewis should be 4. Let's leave that. Hydroxyl radical, and then you can use any of that, but in this video I'm using sodium ethoxide to as a strong base, and the function of this base is simply to deprotonate a carbonyl that has removed proton, forming the enolate. So now let's go right into it, the mechanism proper. So what we'll be doing here is cross aldocondensation, which is the most common, that's between an aldehyde and a ketone. So yeah, this is a cross aldocondensation reaction between propan 2-one and propanal in the presence of a strong base such as sodium ethoxide. So it means that the reaction is going to occur in a basic medium. Now let's run through the basic mechanism. This is just general mechanism for aldocondensation, something that you need to know, especially as people doing chemistry from year 2 above. So the first step is formation of the enolate, or you can say an enol, anyone. Now, typically, when you have a ketone and an aldehyde undergoing cross aldocondensation, well, I would advise you to use the ketone as the enol. Use the ketone to form the enol because ketones are better enol than aldehydes, and that's because due to a stability known as keto-enol tautomerism. That's a story for another day. So we have this ketone that we have here. We have CH3, C double bond O, and we have CH3, and the strong base is sodium ethoxide. Sodium ethoxide. Now, what you need to know is this base will absorb alpha hydrogen. Now, alpha hydrogens are attached to alpha carbon. So like I did last time, if you label this ketone, if this is A, B, and C, so it means that B is the carbonyl carbon. Carbon A and C are the alpha carbons. So these alpha carbons contains 3 alpha hydrogen. So you can take any one. You can take an hydrogen from here. By the way, you are taking a proton. This method is formed by deprotonation. You should know that. You are not taking an hydrogen, you are taking a proton. That's a strong base. Base can absorb proton. Bases are strong bases are proton acceptor. So this sodium ethoxide will take 1 proton. Now let me draw this out for you. We have CH3, C double bond O, CH3, and this base, sodium ethoxide, wants to remove a proton from this carbon. I'm choosing this carbon C now. Now remember, this is a covalent bond. Let's say I'm taking this hydrogen and mark now. This is a covalent bond between carbon and hydrogen. In this bond, carbon brought 1 electron, hydrogen brought 1 electron, they both share it. So this is a covalent bond between carbon and hydrogen. Now carbon brought 1 electron, hydrogen will bring 1 electron, they share it. So this sodium ethoxide wants to take this hydrogen atom as a proton. Thus, it wants the hydrogen atom to leave without its own electron. So if that happens, this hydrogen atom will leave, dropping the electron on this carbon. We will not have this. You have CH3 that we have at the end. Then we have C double bond O. And then we have CH2. Then we have minus. Now, if you see this minus is showing that the electron, this is the electron that this hydrogen left behind. Now, this is what we call an enolate. Enolate, and then the base will hold the proton, forming plus sodium OET, then hydrogen. So that is the first step. And remember, we form this enolate by deprotonation. That's we remove the proton from the ketone, forming the enolate. So that's the first step. Now, Step 2 is the nucleophilic attack between the enolate and the second carbonyl. Between the enolate and the second carbonyl. So let's go. Step 2. We have step 2, which is nucleophilic attack. Nucleophilic attack. And this attack is from this enolate and this other carbonyl. So let's draw the enolate out. We have CH3. We have C double bond O. Then we have CH, the minus. And then plus CH3, C double bond O, H. Now, a very typical case here, a nucleophile wants to attack this carbonyl carbon here. Remember, this is a carbonyl, an aldehyde, and so it has a carbonyl carbon. And as a result, it can undergo nucleophilic attack because the nature of this carbonyl carbon is that it is an electrophile. So what will happen here is this. For this carbon to accept a new group, it must create space for it to come in. And how does that happen? Now, there are two bonds here. Every two bonds in organic chemistry, one is a sigma bond, the other one is a pi bond. That is one. This is one way you can see it. By the way, there's another explanation for this. Now, this pi bond there, pi bonds there that are mobile, they can move. So this pi bond there will move towards oxygen due to electronegativity superiority. That oxygen is more electronegative than carbon. It will move towards it, creating space for this nucleophile to come in. So in terms of arrow terms, showing what will happen. This double bond here will move here. That will create, this is what we call resonance stability, by the way. It will create something that looks like this. CH3, CO minus, then H. This minus is showing this bond and move up. And as a result, this carbon will have a positive charge. Now, why is it having a positive charge? Carbon here has 3 bonds. 1, 2, 3. The bond order of carbon, or carbon has to be connected by 4 bonds before it is stable. So as a result of this nature, this resonance stability, this carbon here become an electrophile. As a result, this carbon here, this nucleophile, can now come and attack this carbon. This is the nucleophilic attack that's going to happen. So there will be a bond between this nucleophilic carbon here, which is the enolate, which is what makes this structure enolate, and this electrophilic carbon. Nucleophile will attack what? Electrophile. So you now have the combined structure. Let me draw it very well. So starting from this place, we have CH3. We have this C double bond O. Then we have this C, we have H, and we have H. And there will be a bond between this carbon and this carbon. So as you draw a bond there between this carbon and this next carbon, we're going to have that bond. This is the bond. Then we have that carbon that has O on top with minus, which is this. Now, once this is negative, by the way, this carbon is acting as a Lewis base. It's donating a pair of electrons. This carbon is acting as a Lewis acid, is accepting a pair of electrons. Once it accepts that, a bond will be formed there, a coordinate covalent bond. So it's going to give you this, and then this carbon is attached to CH3. So we have CH3, and then it has H at the end. Remember, in organic chemistry, there is no order. You can decide to write your own H here and your own CH3 here. It's very correct. So this whole structure that has 2 carbonyl groups, its form in it is what we call an aldo. Although this is not the final product, but this is looking like the final product. This is what we call an aldo. Remember, an aldo is a beta hydroxy ketone. I will show you why it is called beta hydroxy ketone. So if you want to call this a name, you can call this an alkoxide intermediate. An alkoxide intermediate. An alkoxide intermediate. So that is the second step. Now in some textbooks they might say cross aldocondensation has 4 products. No, I've seen textbooks like that. So if you want to number the product, you can say this is product 1, product 2, product 3, and then the fourth product, which is the last step. So the last step is, one thing about organic chemistry is catalyst must be formed at the end of the reaction, or for any proton that is removed, we must find a way to replace it back. Remember, at the first step, we took a proton, so we must find a way to replace it back. So the next step is going to be protonation of this alkoxide intermediate to form the aldo itself, or you can say formation of aldo by protonation. Anyone works. The next step is protonation of this alkoxide intermediate to form the aldo. The alkoxide intermediate, you can call it tetrahedral intermediate. It's fine. Now we want to protonate this whole structure to form the aldo. How do we get this source of proton? Remember, our base, which was sodium hydroxide, held a proton for us. So this proton will be sent back to this. Remember, it's going to be sent as a proton, that's as an hydrogen that lacks an electron, because this is the base. Bases are more electronegative than hydrogen. So to send a proton back to this place, I'm using arrow to show you where it's going to. So the proton is going to this oxygen, forming OH. We now have the final product as HC. We have HC, we have C double bond O. We have C, H, we have C, O, H, and what? H. So this is what we call an aldo. Now, I want to show you, and then plus the base, obviously, you can write it. I want to show you why it is called beta hydroxyketone. Remember earlier in this video, I told you that any carbon that is attached to an alpha carbon is a beta carbon, yeah? And in the carbonyl group, that's a group that has a structure that has CO. Any carbon that's attached to the carbon that has CO is called an alpha carbon. Now, if you look at this structure, let's label this carbon again. We have carbon A, B, C, D, and E. Now, carbon B is a carbonyl carbon, and carbon A and C is attached to carbon D. So carbon A and C, they are called alpha carbon. This is what I have said so far, right? Now remember, any carbon attached to alpha is be beta. Look at carbon D. Carbon D is a beta carbon because it's attached to an alpha carbon, carbon C. So carbon D is a beta carbon. Now what is on carbon D? OH. That one is called beta hydroxy. Beta hydroxy. Now it's a ketone because the carbonyl carbon is not at the terminal, the first carbon or the last carbon. That's why it is called, that's why it is called beta hydroxyl ketone. So that's just the simple mechanism of forming an aldo. By the way, this will be the fourth product if you are counting it. The fourth product of the cross aldocondensation. Now, I'll give you something to try. Let's give our users to try. Feel free to, you can draw it in your paper and just post a snap on it on the comment section. An aldocondensation reaction between two, okay, let me write it here. So an aldocondensation reaction between CH3, this is a practice question, between CH3, C double bond O, CH2, CH3, and let's use benzaldehyde and benzaldehyde. C double bond O, H, and benzaldehyde using hydroxy radical as the base, using hydroxy radical as the base. So simple, just follow the steps I've given in this video and you see that you get your aldo, which is the beta hydroxy ketone. So feel free to do it, snap the answer and send it, right? Send it during the comment section. So thank you for your time. Thank you for watching, and remain mastermind of air science.